Welcome to the Deep Dive. Today, we're hitting the gas on a topic that really felt like sci-fi just a few years back. Autonomous vehicles.
Yeah, absolutely.
It's easy to picture a car just, cruising along by itself. But the stuff happening behind the scenes to make it safe, make it smooth, that's a huge challenge.
It really is. Think about it, teaching a car to see, think, and react almost like a human driver, but hopefully better, right? Superhuman precision, no distractions from texts.
Right. No checking phones.
Exactly. It takes some seriously clever engineering.
And that's what we're digging into today. We've got this great collection of research looking at kind of the two main brains being developed for these self-driving systems.
Model predictive control, MPC, and then, well, a whole bunch of reinforcement learning methods.
Yeah, RL. So think of this as like your quick guide to how these actually work. What are their strengths? What are their weaknesses? And what's really exciting, how they're being combined.
For the cutting edge stuff.
Exactly. Our goal here is to give you that inside track, without making you feel like you need a PhD in robotics to follow along, ready to sort of peel back the layers.
Definitely. Let's do it.
All right, let's jump into model predictive control first. MPC. Sounds technical, right? But the basic idea is actually quite intuitive. So maybe in a nutshell, what is MPC?
Okay, so at its heart, MPC is really about smart forecasting. Imagine the self-driving car needs to make its next move. MPC predicts how the car is likely to behave in the, let's say, near future based on where it is now and what it could do. Then it uses some complex math.
The tricky bit.
The tricky bit, yeah. To figure out the absolute best sequence of actions to take right now to reach a goal. Maybe that's staying in the lane, hitting a target speed,
Okay.
while obeying a whole set of rules. And this is key. Things like speed limits, the car's own physical limits, and, most importantly, safety boundaries.
So it's like the car is constantly running what-if scenarios to find the safest, most efficient way forward.
Precisely. And here's something interesting. MPC isn't brand new, not just for cars. It's been a kind of secret sauce in industries like petrochemical plants for decades.
Really? Why there?
Well, because in those fields, running processes right near their limits often means maximum efficiency. And MPC is brilliant at handling those tight constraints.
Oh, okay.
So that same ability to respect limits that keeps a refinery efficient, that's now making sure your self-driving car doesn't decide to ignore a stop sign or try to turn too sharply.
That really puts it in perspective. Okay, so how does this prediction and respecting limits thing translate into actually making a car drive?
Right. So autonomous vehicles use MPC in quite a few ways. Path following is a big one, just making sure the car sticks to the route. Obstacle avoidance is another critical one. MPC calculates the exact steering, the braking needed to avoid hitting things.
Yeah.
Absolutely. And just general motion control, coordinating the steering, gas, brakes smoothly. The research we looked at shows it being used in single cars, but also in groups like those AGVs,
Right.
automated guided vehicles, in warehouses.
Oh, yeah, those little robot carts.
Exactly. MPC helps coordinate them too.
Can you give us maybe a couple of specific examples from the research, how they're using MPC?
Sure. One study tweaked a version called MPCC Model Predictive Contouring Control. Now, contouring control is specifically for following curved paths really precisely. Think like a racing line.
Oh, okay, for performance.
Exactly. They optimized it to help autonomous race cars stick to that perfect line, pushing the limits but staying on track. Another paper talked about using MPC for both planning the path and following it, building in algorithms to spot and steer around obstacles in real time.
Yeah.
And here's a really interesting angle. MPC often acts as a safety net. So you might have a higher level system, maybe using RL, we'll get to that, making a decision about where to go.
Like the strategic planner.
Sort of, yeah. But the low level MPC controller can step in and say, hold on, that move isn't safe, or that violates the car's limits, it enforces the rules.
So MPC is like the responsible adult supervisor for the more adventurous AI?
That's a pretty good analogy, actually, yeah. And our sources also mention coordinating multiple vehicles using something called distributed MPC, or DMPC.
Okay, what's that?
Imagine a fleet of self-driving delivery vans. DMPC lets each van make its own decisions, but also talk to the others, coordinate, avoid all trying to use the same road, prevent traffic jams among themselves.
Wow.
Of course, that brings its own challenges, right? Making sure they share info correctly, reach a consensus. It's complex.
So like a massive coordination puzzle on wheels.
Yeah.
Any other tricks researchers use with MPC to kind of refine the car's behavior?
Yeah, they're adapting it too. For instance, by adjusting the weights in the MPC calculations. That basically tells the system what's most important right now. Is it speed? Is it staying perfectly centered? You can tweak that balance.
So you can prioritize different things depending on the situation.
Exactly. There's also work on using multiple models that adapt, like handling uncertainty about how much grip the tires have. That changes with weather, road surface.
Right, that's a big one.
Huge. And another clever idea is using a target safe speed profile. This is worked out based on things like how sharp the upcoming curve is, the estimated road friction,
Okay.
and the MPC aims for that sensible speed instead of always trying to push right to the absolute limit of the car's handling.
That sounds much smoother, probably safer too. Seems like MPC is really versatile, but there must be downsides, right? Hurdles.
Oh, definitely. A big one is the computation. Solving those optimization problems, figuring out the best move, takes serious processing power, especially in real time for complex situations.
Yeah, I can imagine. The car doesn't have minutes to decide.
Exactly, milliseconds count. But the field is pushing forward. There are more efficient methods emerging, like explicit MPC.
Explicit MPC.
Yeah, think of it like pre-calculating the optimal control move for a huge number of possible situations beforehand. So when a situation comes up, the answer is already there, like looking it up in a giant playbook. Much faster.
So it's like the car do its homework for almost any scenario.
Kind of, yeah.
Yeah.
In a way. Another really critical point is model accuracy. MPC is only as good as the model it uses to predict the future.
Garbage in, garbage out.
Pretty much. If the car's understanding of itself or the road is off, its predictions are wrong, and the control won't be optimal, maybe not even safe. That's why there's a lot of research into using data-driven models, even neural networks, within MPC to make those models more accurate.
So blending traditional engineering with cutting-edge AI.
Exactly, that blend. And, it's worth mentioning there's still some debate. Is MPC always better than more classic control methods? Some studies found the improvements weren't massive in certain cases. The benefits sometimes came more from how easily MPC handles constraints or how intuitive it is to tune, rather than it being fundamentally superior across the board. And finally, just ensuring the whole thing is stable, feasible, robust. That's paramount. Researchers use specific techniques to guarantee the system behaves predictably.
Okay, so MPC predicts, optimizes, plays by the rules, getting faster and smarter. Got it. Now, let's completely shift gears. Reinforcement learning, RL. What's the core idea here? It sounds very different.
It is fundamentally different, yeah.
Yeah.
Instead of writing explicit rules, with RL you have an agent. That's the car's control system.
Right.
Learning through interaction with its environment, the road, other cars, pedestrians, everything.
Right.
The agent tries an action, say, turning the wheel slightly. Then it gets feedback or reward if that was a good move, maybe moving it closer to the goal, or a penalty if it was bad, like getting too close to a curb.
Learning by consequences.
Exactly. Over lots and lots of trials, this trial and error process lets the agent learn an optimal policy. That's basically its strategy for choosing the best action in any situation to get the most reward over time. Forget coding every single rule. RL lets the car learn how to drive, maybe a bit like humans do, through experience.
So it's like a video game character learning the best moves by getting points for success and, well, losing points for crashing.
That's a perfect analogy, actually. And it's different from supervised learning, where you show it examples of correct driving, or unsupervised learning, where it just looks for patterns. RL is active learning through feedback.
Super interesting. So how are researchers actually using RL to make cars drive? What kinds of algorithms are involved? It sounds like there might be a few.
Oh, yeah, there's a whole zoo of them. A popular one is deep Q networks, or DQN. These use deep neural networks to estimate how valuable different actions are in different situations. And there are enhanced versions like dual DQN, prioritized experience replay, which helps it learn more efficiently by focusing on surprising or important past experiences.
Right.
There's even something called PERD2MQN, which is like a super optimized DQN aimed at learning tricky local maneuvers, like getting around clutter really quickly and stably. These newer versions show real gains in learning speed and performance.
Wow. Okay. Lots of acronyms, but the trend is towards faster, more stable learning for immediate situations. Yeah.
That's a good way to put it. Then you have algorithms for continuous actions, things like the precise steering angle or how much brake pressure, things that aren't just left or right, but a whole range.
Smooth adjustments.
Exactly. Deep Deterministic Policy Gradient, or DDPG, is one for that. It's been used for things like lane keeping, obstacle avoidance on highways and simulations. Seems pretty stable, learns well.
So DQN for maybe bigger decisions, DDPG for the fine control, roughly.
Roughly, yeah, though the lines can blur. But wait, there's more. Proximal Policy Optimization, PPO, is another big one. Often used for planning longer routes, more complex paths.
Okay.
They're doing interesting things with it, like using a beta policy to help it explore actions within sensible limits, and using distributed computing to speed up learning. We've even seen PPO combined with older methods like pure pursuit for better path tracking.
Combine old and new again.
Yeah, trying to get the best of both. Controllers trained with PPO have shown they can learn pretty impressive evasive maneuvers around sudden obstacles in simulations.
Trying to build a really well-rounded driver AI.
That's the goal. And you also have imitation learning playing a role, where the RL agent learns by watching an expert, a human driver, basically getting a head start by copying good behavior.
Makes sense. Learn from the best. So what information does the RL system actually use? What's the car seeing or feeling?
That's the state space. It can vary a lot. Usually it's sensor reading speed, angles, distances to things from LiDAR or radar, sometimes even raw camera images. One DQN study used camera and laser data for navigating cities. Think of the state as the car's complete picture of its situation right now. The better the picture, the better the decision.
And the rewards and penalties. How do they define what's good driving? That seems critical.
Absolutely critical. Designing the reward function is maybe one of the hardest parts. You need to incentivize what you actually want.
Right.
So positive rewards for reaching the goal, staying in lane, keeping safe distances, penalties for collisions, going off-road, maybe even for jerky movements like unnecessary sharp turns.
You have to be really careful what you wish for, or what you reward, I guess.
Exactly. It's a delicate balance. Too simple, the AI finds loopholes. Too complex, it might struggle to learn anything useful. It's like trying to write the perfect rules for a game.
Tricky.
Definitely. And then there's the classic RL challenge. Exploration versus exploitation. Does the agent stick with what it knows works, exploit, or does it try new things, potentially risky things, to see if there's a better way to explore?
You need both. Techniques like epsilon greedy, where it takes a random action, sometimes help manage that.
Okay.
And finally, experience replay buffers are really important. Storing past experiences and learning from them again later helps stabilize the learning and makes it more efficient.
This is all fascinating, but we always hear about safety and human oversight with autonomous tech. How does that fit with RL, which sounds a bit like letting the AI figure things out on its own?
That's a great point, and it leads us to human-in-the-loop reinforcement learning, or HILRL.
Okay, human in the loop. Sounds promising.
The idea is to bring human input directly into the training. This isn't just letting it learn totally alone. It could be a human driver taking over when the AI struggles.
Intervention.
Right. Or providing demonstrations of good driving, or even just giving feedback like thumbs up, thumbs down on the AI's actions.
So the AI learns from its own experience and from direct human guidance. Exactly. And that can be huge for guiding the learning, making it safer, and making sure the final driving style feels, well, human-like and acceptable. There are frameworks like SafeHill RL that even have safety modules checking human interventions before handing control back to the AI.
Wow.
And there's even cooler stuff like physics-enhanced RL with human feedback, PERLHF. That combines human input with physics models for safer learning, sometimes without even needing an explicit reward function. The human feedback is the reward signal, in a way.
Learning just from human correction and physics, that's pretty advanced.
It is. And there are ideas like PEHI, physics-enhanced human-AI collaboration, human and AI driving policies running side by side, and a decider picks the safest action moment by moment. Digital twins, virtual copies, are also used here for training and testing this shared control safely.
Okay, so we've got MPC, predictive, constrained, good math backbone. And RL learns from experience, adaptable, can incorporate human feedback, it feels like. The next step has to be putting them together, right?
Absolutely. That's definitely where a lot of the cutting-edge research is heading, integrating MPC and RL to get the best of both worlds.
How does that work in practice?
Well, a common approach is hierarchical. You might have a high-level RL planner maybe using DDPG, figuring out the big picture. the route, the
Yeah.
target speeds through different sections.
The strategy layer.
Exactly. And then a low-level MPC controller takes those goals and handles the precise second-by-second control of the steering, acceleration, braking, making sure it's all done safely and within the car's physical limits.
So RL is the brain, MPC is the spinal cord handling the reflexes safely.
That's a really good way to put it, yes. Researchers are looking at these hierarchical setups for personalized control too, adapting to different driver preferences. And sometimes RL is even used to tune the MPC controller itself, like learning the best settings for MPC in different conditions.
Using AI to optimize the optimizer?
Pretty much. It seems like this combination can really tackle the limitations of each method on its own.
How so?
Well, RL's ability to learn from experience can help overcome MPC's challenges when the environment is really unpredictable or the models aren't perfect. An MPC provides that crucial safety layer and a degree of interpretability that pure RL, which can sometimes be a black box, might lack. You have the guarantees of MPC underpinning the learned behavior of RL.
This has been, wow, a really fantastic deep dive into how these cars are learning to think. So let's try to wrap up. What are the main takeaways for everyone listening?
Okay, I think the big picture is MPC excels where you need prediction, optimization, and strict adherence to rules and constraints. It's solid, mathematically grounded.
Right.
Reinforcement learning, on the other hand, is incredibly powerful for learning complex, nuanced behaviors directly from data and interaction, especially with that human-in-the-loop element for safety and refinement.
And the future is likely both.
It really looks that way. Combining them, maybe RL for the high-level strategy and learning, MPC for the low-level execution and safety net, seems like a really promising direction for getting autonomous systems that are robust, safe, but also adaptable.
And clearly this isn't solved yet. Lots of ongoing work.
Oh, absolutely. Making these things computationally efficient enough for real cars, strengthening the safety guarantees, especially with human interaction, and just tons of real-world testing and validation, that's critical.
So as this tech keeps evolving, blending these approaches, maybe a final thought for you listening. How will this changing partnership between human guidance and ever smarter AI systems ultimately shape how we trust them and, the whole future of how we get around? Definitely something to ponder.
Indeed. And if this has sparked your interest, we definitely encourage you to check out some of the research papers. There's so much fascinating detail we couldn't cover on the specific methods for MPC and RL and autonomous driving.
Thanks so much for joining us on this deep dive. We'll catch you next time.